Hi guys, today we're going to look at the center of mass of a system of particles, and we are going to also relate this back to our total momentum from last video. So let's start out by defining our center of mass, and this is basically to say if we have some system of particles here, it could be any number of particles, we can define the center of mass as a point in space here, which we can find by the following relation. So that's to say our center of mass position, so it's a vector that points to this point in space, is just defined as sum of mi ri divided by the sum of mi. So this is to say if we have any number of particles, to find the center of mass, we look at each particle individually, we multiply its mass by its position, we add up all of those together here, and then we divide by our total mass. So you see here this is a vector, so this will be some point in space here, and therefore our r, center of mass, is just going to be a vector pointing to that point in space defined by this relation. So this is good, and this is something you'll see how to solve for given some real numbers today. But now we want to also talk about why is this a special point. Right? Just if you're just told to solve for the center of mass, that's fine, but this is a very special point in space. And the reason it's special is that we can think about this system of many particles as if it were just one particle acting at that center of mass. So that's to say the center of mass for this system is going to move as if it were just one single particle acting here with mass equal to big M, which is just the total mass, meaning the sum of all of the little masses. So instead of having to worry about every little particle, we're just going to think of one composite particle of a total mass, big M, acting at the center of mass that we just solved for. So in terms of our momentum that we talked about last time, we defined our momentum before, our total momentum for a system, equal to P1 plus P2 plus ... and this is a vector, right? So we had this definition before, but this is going to get cumbersome if we have a lot of particles acting. So for instance, if we have some number of particles, maybe we're looking at a rigid body and we're looking at the system as all of the atoms in that body. So this is going to get very cumbersome. And so something we can do is utilize this fact that all of this is going to break down to a composite particle by redefining our total momentum. Instead of looking at each individual momentum, we can redefine this looking at the composite particle, which has mass big M, and it's going to have a velocity times the velocity of the center of mass of this whole system of particles. So now we have our definition for total momentum, which really only looks at this composite particle. So we're going to utilize our information about the center of mass here to not have to worry about many, many, many particles and just worry about our total mass acting at the center of mass that we defined for, and that will have some velocity center of mass. So we'll see how this is used today. So let's look at the problem statement here, and that reads as follows. A 45 kilogram woman stands up in a 60 kilogram canoe 5 meters long. She walks from a point 1 meter from one end to a point 1 meter from the other end. If you ignore resistance to motion of the canoe in the water, how far does the canoe move during this process? At this point, you should pause the video, reread this problem a couple times, and maybe even try it on your own. Okay, so we have our scenario drawn out over here. So this here is just our initial scenario where the woman is standing at some point on the canoe, and they tell us that's 1 meter here from the left edge. So we're going to define our zero position to be this initial left edge of the canoe. And so we want to recall once we define this, this has to be our zero position at all times. So what they tell us happens is the woman is going to walk to the right on the canoe, and whenever she walks to the right on the canoe, that is going to push the canoe itself back to the left. So we can see that by Newton's third law. As soon as she pushes the canoe to the left, the canoe is going to push her to the right, and both objects are going to move in the opposite direction. And so in this scenario, we're going to end up at some configuration, which we really don't know much about, but in some configuration, the woman will certainly be to 1 meter to the left of the right edge of the canoe. And then other than that, we can really just sort of look at the diagram, and we don't know any of these distances in particular with respect to each other. So we want to solve for the distance that the canoe itself is going to move to the left. So this seems a little bit tricky. We're really not given much information. So our first step here is to think about the momentum of this system. And so in this case, the system will be the canoe and the woman, and those will be the two objects that are in our system. And so if those are our two objects, there is going to be no net external force, right? The water itself is frictionless, so nothing else is acting on these two objects here. And so therefore, our momentum is conserved. So that's to say our total momentum, which we defined at the beginning of this video now as the total mass of our system times the center of mass velocity, this total momentum is going to be constant. That's what it means for momentum to be conserved. And so we can actually say something even a little bit stronger, right? We can say that the total mass times the center of mass velocity is the same at all times, it's constant, but also it starts at rest. So our center of mass velocity starts at 0, and so if it starts at 0, it's going to have to remain at 0 at all times. So this actually is a very important step in that we can now say the center of mass velocity is going to be 0 at all times in this system's motion. And so our special point, the center of mass, its velocity is 0. And so even further, we can recall a velocity is basically just equal to d dt of that position. So in this case, our center of mass position, which is something we can solve for directly, the d dt here, so the change with time, is going to be equal to 0. So this is something you want to make sure you understand. So go ahead and pause the video if you need a couple seconds to think about this. But what this is going to then eventually tell us is that our velocity of our center of mass is 0. So our center of mass itself must be constant. So whatever our center of mass starts at, whatever this position starts at, it's going to stay the same. So at our final scenario, our center of mass of the system will be in the same position. So we see here, initially maybe the center of mass will be somewhere between the person and the canoe, so it might be at some point right around here. And in our final scenario, that should be the same. The system, of course, both constituents of the system have moved, but the center of mass of the system itself should not have moved. So center of mass is constant, and so now we can see sort of a way to solve this problem, which is to say we can solve for the initial center of mass. And from here we see we have our masses and our positions, so we can solve directly for that initial center of mass, and then we can impose that on our final scenario. So let's go ahead and start off by doing that. So in our initial scenario, we have the center of mass is going to be equal to the mass of the woman times the position of the woman initial, and then that will be plus the mass of the canoe times the position of the canoe initial. And then all of this will be divided by our total mass, which is just to say, and this will remain constant at all times. So that's just the mass of the woman plus the mass of the canoe. So this right here, at this moment, we can solve for this as long as we assume that x equals 0 is the left edge of our canoe. We see the woman is 1 meter to the right of that. And so I'll let you guys follow along your solutions, but this right here just amounts to plugging in some numbers that we know. And so once we do that, we should get that our center of mass is just going to be 1.86 meters to the right of our edge of our initial canoe position. So that's to say that we could, go along 1.86 meters and draw this center of mass position. Maybe it's somewhere like right here. And then it's going to have to remain constant in the final scenario too. So for our final scenario, I'll draw this over here a little bit and give myself some room. But for our final scenario, we know the center of mass must still equal 1.86. So I'm going to write 1.86 is still the center of mass. But now our position we see of the woman and the canoe have both changed. They've sort of swapped, and we don't really know how far the distances that they've moved are, but we can solve that now by setting our final center of mass equal to 1.86. So we're going to go ahead and we're going to play the same game here. We'll set up the same relation, but now our positions have changed. So we still have the mass of the woman, and in this case now we want the position of the woman final. And again, same with the canoe. We have the same mass, but the canoe final position will now be different. All of this will still be divided by our same total mass, which is just mass of the woman plus mass of the canoe. So now we have this relation, and we can set it equal to our known center of mass. And again, we don't know our positions. So in this equation, we now are not quite there yet because we have two unknowns, unfortunately. And we'd like to solve for really the position of the canoe, because if we get the final position of the canoe, we can just subtract the initial position and get our change. And so here we need to find one further relation, and we can do that by sort of looking at this final scenario. And so this is something that you'll want to pause the video and make sure you can get to. But what is going to happen if we look at this scenario down here is that the position of our woman, and so let me write that here, our woman's final position is going to be equal to the position of the canoe plus 1.5 meters. So that will be equal to the canoe's final position plus 1.5. That's to say we're told that the woman ends up 1 meter to the left of the edge of the canoe, and that itself, by definition of how this canoe was set up, is going to be 1.5 meters to the right of the center of mass of the canoe. So here we have our relation saying that the woman should end up 1.5 meters to the right of the center of mass of the canoe. So this here is going to be what we'll use, and we see at this point we can sort of get to our answer by just plugging in x woman final equals x canoe final plus 1.5. We plug that in right here, and then we can solve this guy for the x of the canoe final. So I'll let you guys do that at home. And what you should get, if you look at the solutions and follow along, is that the canoe ends up at a final position of 1.21 meters. So that's to say that the canoe here, from our 0 point, which we defined as this edge here, is going to be 1.21 meters to the right. So we see our scale was not necessarily great here, but perhaps the canoe should be pushed to the left a little bit. But it served its purpose. So now what we want really is the total change in position of the canoe, which just amounts to x canoe final minus x canoe initial. So we can plug in our variables. 1.21 minus the canoe initial would be 1.5 plus 1. So that would be 1.21 minus 2.5. And we will get to our final answer of minus 1.29 meters. So this is to say that our canoe's position has changed in the negative direction, so it's moved to the left, which is good, and the amount is 1.29 meters. So let's go ahead and review what we've just done. We first defined our system as being comprised of the woman in the canoe. Because there are no external forces on that system, the total momentum is conserved, which led to the fact that the center of mass position would be constant at all times. So we solved the initial scenario for the center of mass, and then imposed that position as the center of mass in the final scenario. And then we used the relation between the position of the woman in the final scenario to the position of the canoe, and solved directly for the final position of the canoe. And so this led us to find the change in its position. Okay, so I hope this problem helped you guys, and I hope it gave you an idea of how to use this sort of seemingly abstract concept of the center of mass to solve a very concrete physics problem. So if you guys have any comments about this video or any of the videos, please leave those on the links section for comments, which should be to the right of the video links. Thanks for watching.